In this video, we're going to look at finding the range of a function. Let's first recap the terms domain and range. The domain is the input set, or the independent variables. The range is the output set, or the dependent variables. So let's say we had a function of x, and we had y is equal to the f of x. And we define the f of x to be a simple linear function, 2x plus 1. If we drew this now, and I'm going to draw this for all real values, we would have now a straight line. So let's go ahead and do that. So let's put that on. It would do something like so. So we could now say that y is equal to the f of x. So y is equal to the f of x. We could say now the domain, and writing this here, the domain are all of the values along the x-axis that we can put in. So we'd say that the domain x belongs to the reals. And we looked at this in the last video. So if I now had, for example, the f of 1, if I did the f of 1, 1 now comes from the domain. So I'm choosing a number for x, and I'm now putting this through the function. So if we did that, we'd have two lots of 1 plus 1. This is 3. So we can say that 1 is in the domain, so in the domain, and we can say now that 3 is in the range, so in the range. So I'm subbing now the independent variable in, and I'm getting the dependent one out. Finding the range of a function can be quite tricky. What we're going to do in the video is look at a range of different techniques, some of which you'll use in combination with others, to find the range of a function. So if y is a function of x, the range will be all of the numbers that we can see now up and down the y-axis. So let's consider now this one-to-one function. We've not restricted the domain. So we said the domain belongs to reals. It's all real numbers. So I can choose any number along this x-axis. So here is the x-axis. This is our independent variable, the one I choose, and then now it gives us a value of y. So if I think now, if I looked up and down the y-axis, I would see now all real numbers. So what we could say at this point right here, we've got x now belongs to the reals, and we could say now that y also now belongs to the reals. So I'd write it like so, y belongs to reals. So this is the range of the function if we haven't restricted the domain. Now we might want to restrict the domain. So for example, we might say now the domain, let's look at the domain. So let's say the domain, x was going to be, and I'll write it like so, we've got x between 1 and let's say we've got 3. If I did this now, I'd have, and I'd redraw the part that we're interested in, we're only now looking from 1 to 3, which is going to be this portion of the line. So if I did the f of 1, if I put 1 in, we've got this point right here, which is going to be 1, 3. If I now did the f of 3, we're going to have 3, 7. So when I look up and down the y-axis, I can see the values of 3 and now up to 7. So this part right here is only giving me values between these. So we could say now that the range, and we could write it like two different ways. We could say that y is going to be greater or equal to 3, yet in turn less or equal to 7. Or alternatively, if we write this out, this now is the range. So I've restricted the domain. We could say the f of x is going to be between 3 and 7 inclusive. So they're two different ways of writing it. So when we have this one-to-one function, a quick sketch helps us now establish what the range is, whether we've got now a range, a domain where we've got all real numbers, or where we've restricted the domain. So anytime you're given a question like this, a quick sketch can help. And testing the endpoints of this particular one-to-one function will give us now the range. Testing the endpoints of the domain doesn't always give us a range, as we'll see shortly. But in this particular case, the sketch, plug in now f of 1, which is now the lower value of the domain, and f of 3 gives us those values. So in this particular example, we can see a nice sketch helps us. Let's look at other examples of where a sketch will help. So let's say we define the f of x this time. Let's go for y is equal to the f of x, and let's say now, so this is going to be my graph, y equals the f of x, and we can say the f of x is equal to 2 to the power of x. We will say now the domain, let's write the domain, we can say that x belongs to the reals. So this can take any number along the x-axis, and we want to know now what values it's going to give me in terms of the y coordinates. So if we drew this now, what we've got is something that looks like so. So it's going to be an exponential graph, and it will grow very rapidly after this point. So the question is now, what values would I see if I went up and down now the y-axis? We could say at this point now that if we said y is equal to the f of x, so let's say y is equal to the f of x, we could say that y is going to be strictly greater than 0. We can see now that this is going to give us all values greater than 0. It can't be 0. 2 to the x can never be equal to 0. So we're looking now that y is going to be greater. And we can just simply now look at the graph and say that's what's going to happen. So a quick sketch has helped us out in that particular case. If we wanted to restrict the domain, let's say now that the domain, let's say that x was going to be between, let's go for -1 and let's say 2. So that now is, let's put the domain, so the domain will be all real values. We're going to take now, instead of the all real values here, we're going to take from -1 now to +2. So if I look at that, it's a 1-to-1 function now in that particular interval. So let's put these 2 points here. So it'll look something, let's have it something like that. So now what we've got here is -1 and we've got 2 just here. It's not a massively accurate sketch, but hopefully that'll give you some idea. So we can see now that the range is going to give us this portion of the curve from the point here to here. So all we need to do is consider the end points. So if I did now the f, and let's write this in, f of -1, 2 to the -1 is going to give me now 1/2 or 1/2. And then if we did the f of 2, so remember, this is my independent variable. This is giving rise now to the dependent variable. If I put in 2, we're going to get 2 to the power 2, which is going to be 4. So we could now say that the range y is going to be between 1/2 and 4. So by restricting the domain and a quick sketch, we can see how that works. Let's look at another example. Let's go for now a reciprocal graph. So let's do the f of x. Let's write this here. Let's say y is equal to the f of x, and we'll let the f of x be, let's just go for 1/x. So f of x is equal to 1/x. So if we graph this now, we've got y is equal to the f of x. We've got now values of x, and we've got values of y. For this to be a function, every element in the domain must give rise to one and one only value in the range. Therefore, we need to restrict the domain. So we can say the domain is going to be all real numbers, so x belongs to the reals, but we can say that x cannot be equal to 0. We can't divide by 0, so we just restrict the domain. So 0 is not included. Now, if we drew this, we would have the following. So it looks something like so, and then the other side, we would have something like so. So we've got now the asymptotes, the x and the y-axis. So if I went now up and down the y-axis, what values would I see? Well, I'd see all values other than y being equal to 0. So we could go right the way up, positive and negative infinity. We would tend to those values. So let's go ahead and say now that if the domain is x belongs to reals where x can't be equal to 0, we can say the range, we can now say that y belongs to the reals, so y belongs to the reals, and we can say that y cannot be equal to 0. So a quick sketch again, and our understanding that now the restricted domain will give us the range. If we looked at a slight alteration, and let's say we have now the f of x, let's switch this up a bit, so we had a different function, and you might want to call this a g of x. You might see g of x, you might see h of x. I'm going to just stick with f of x. Let's say the f of x was going to be 4 plus 5/x. So if we consider again a sketch of this, and in this case let's restrict the domain. Let's say now that x is going to be, so this is the domain, we say x is going to be now greater, and we'll make it strictly greater than 0. Let's go ahead, let's make this strictly greater than 0. We can't now have 0, so we can't divide by 0, so it's going to be strictly greater than 0. Now if we drew this here, we would have the following. So this is just another reciprocal function, but we've now increased the values here by 4, so we've added 4. So if I put the asymptote on here, we would have something that looked like that. So that now is the line y is equal to 4. So if we do now y is equal to 4, and I drew this, and we're interested now in greater than 0, so it's just this portion of the curve. So we can see from here that it's going to tend now to this line right here, and it will go there, and it will go on and so on and so forth. So these are values of x, and then now we've got values of y. So what can we say about the range of the function? We can simply state now that the range, or f of x, and we'll write it just here, f of x will always be now greater than 4. And we can see that. We can see that that is never going to touch the line y is equal to 4, and then it's going to get very big now as we get close to values of 0 for x. So again, a sketch is going to help us out. So this now is the range given that the domain was restricted, and we simply graphed it and gone from there. Again, if you want to think about this like so, let's grab this up, and I appreciate this. In fact, I'll just do a different color. If we look now at all values that we would see now up and down the y-axis, we can see now that we're going to start just here, which is going to be 4, and then we're going to move upwards. 4 is not included in this. We might be given a slightly different function. We might be given what we call a piecewise function. So if we look at now the f of x, and we will define the f of x, let's go for, let's have now 2x, and we will say now 2x are for x, and we will have x is going to be between -1, and let's go to 3, and then let's say we've got now x plus, let's do x plus 3, and let's say we've got now 3, and then we've got now x, and then let's go up to, let's say we're going to go up to 8. So this is what we call a piecewise function, and we could draw this in 2 sections. So we've got 2 linear functions, and we would have now 2x. So 2x is going to be from -1 to +3. So let's say it's going to go from there to just here. So that'll be like so, and that's going to be now, and I'll just put this through the origin shortly. That's going to do something like that. So let's move that there. So that's from -1 now to 3. So let's put -1 here. So that's going to be now -1, and then this point is going to be 3. Then what we're going to get now is this linear function of x plus 3, and we're going to go now up to 8. So let's go up to 8. So this is going to be a slightly, well, half the gradient, and it'll look something like that. So let's go ahead and extend this up. So this is just a rough idea of what we're going to get. So let's do that, and we'll put this point just here. Let's say that point's going to be 8. So this now is 2 different functions, and let's just extend that, and it'll look something like that. So what we might want to do now is find the range. If we look at this from the side, what we're going to have, the range are going to be the values of y that we can see in this particular interval here. So let's say that this is going to be y, let's say that's going to be y, and let's say that this is going to now be x. So what we're interested in is these numbers right here. As it's now a linear function, we can simply test the endpoints. So for this particular one, now if I've got the f now of -1, that needs to go through the first one. So I'm taking now a value from the domain. As -1 is in the 2x part, I'm going to get now -2. If I consider this endpoint right here, 8 is in the second part, so we can see now that if I do the f of 8, I'm going to end up with 8 plus 3, which is going to be 11. If you consider now 3, just here we get 6, and just here we get 6, and you can see where they match up. So what we've got then is this point right here. Now it's not massively accurate in terms of its scale, but that point is going to be -2, and then this point up here is going to be 11. So we could say now that the range of this particular function, the f of x, is going to be between -2 and 11. And you can see now from the sketch, that's what we're going to get. So that's another example where you might be asked to find the range given this piecewise function. What I now want to do is move on to looking at quadratics, as there's a couple of different ways that we could deal with quadratics. So let's have a look now at a quadratic equation, and we could say now the f of x is equal to x squared plus 1. I always suggest that you draw a sketch. If the function is completely alien to you, then you're going to struggle. But this is one that we know from here. So if we look at this right now, we've got the function like so. So this is what we call a many-to-one function. So we know that -2 is going to give us now 5, and we also know that 2 is going to give us 5. We know this point here is going to be 0, 1. So if we consider now x, and we'll say that the domain, let's say the domain is going to now be on here, x belongs to the reals. So if it belongs to reals, we can see now that the f of x is going to be greater or equal now to 1. So we can see from the graph, so if I went up now the y-axis, we would see that that's going to be all real values up there like so, and we're just going to keep going up, and then we will have now this minimum point now at 0, 1. So the sketch has helped us out. So we could say f of x is going to be at least 1, or we can say that the range y, if we define this to be y is equal to the f of x, we can say now that y is going to be at least 1. So that's what we'd have. Do be careful if you've got a negative quadratic though. Consider now a negative quadratic. If we went the other way round, we would be looking at this to be now a maximum point rather than the minimum point. So we would be considering now all of the values down this way. So that's why the sketch can help us out. Let's say I went ahead and restricted now the domain of this function. Let's say we had now the domain, so let's write the domain, and we said that x was going to be between, let's go for now -2, and then we're going to go for 2. This now isn't a one-to-one function. It's a many-to-one function. If we look now at plugging in -2, we're going to end up with 5. If I plug in 2, we're going to end up with 5, which suggests now that the range of this is going to be now 5. That's clearly not the case from the sketch, and there are a couple of different ways that we can deal with quadratics. One of those ways is to complete the square. So when we're looking at the range of a function, if we've got a quadratic, completing the square can help. So let's say we had now, let's go for f of x. So f of x is going to be, let's say we've got x squared minus 4x, and then we had, let's say on here we went for minus 12. So this now is a quadratic, and if we sketch this up, let's look at what we've got. So we'd have the following scenario. So can we factor that? Let's draw a quick accurate sketch. So we're going to have x minus 6, and then we're going to have x plus 2. That looks like it's going to factor. So what we'd have now is the following here. So we'd have something that looked a bit like this. So we would now do something like so. Let's do that, and then we'd come around and it would do that. So what we've got then is this point is going to be -2, and this point is going to be +6. What we want to do is find now the range of this function. So let's say the domain was not restricted. So I didn't restrict the domain. We said that x belongs to the reals. So again, quite clearly testing the endpoints is not an option. What we can do here is go ahead and simply now complete the square. So we could say in completed square form, f of x is going to be x minus 2 all squared. Then we're going to have -4 minus now the 12, which will give me -16. So this point down here, it's not a massively accurate sketch. It's going to give us now my axis of symmetry like so. So what we're going to have, and then we're going to have our minimum point or vertex. And this is going to be 2, -16. So that's what we've got. Now, if we think about the range of this function, so if we went up and down the y-axis, what would we see? Well, we would see now this. We would see all values greater now than -16, and we could go up from this point right here, and then it goes straight up. So what we could say now from here, if we said that y is the function of x, and that's x squared minus 4x minus 12, we can say now that y is going to be greater or equal to -16. That's the minimum point right there. So we can see by completing the square that that is going to be what we have. So as we can see, testing the endpoints isn't sufficient. And another example of this might be, let's go ahead and do this. Let's say we had now, let's say y is equal to the f of x. Let's say now f of x, let's go for f of x is going to be equal to x squared minus 1. And now we might say that the domain, let's restrict the domain. Let's say the domain, we had now x, and x was going to be between, let's take now -1, and let's take 3. So this now is my domain. So if I sketch this up, what we've got now is a quadratic. X squared minus 1 greater than now 0, or greater or equal to 0, look like that. And then we will come the other side. Now I've restricted the domain on this. So if we put in, let's say we put in -1. If I put in now -1, f of -1 is going to give me 0. So what we've got then is this point right here, and we can see that's 0. And then we've got this point down here, which is going to be -1. And then we're going to have this point right here. So if I did now the f of 3, I'm going to get 8. So that's going to be the point 8, or 3, 8 if you like. So we can see now that by restricting the domain, it would be foolish just to test the endpoints, because it's telling me now if I test the endpoints that the range is between 0 and 8. Quite clearly it's not, because I've got the minimum point down here, so we'd have to now consider these values. So do check, and a sketch will help, because in this particular region it is now a one-to-one function. Here it isn't a one-to-one function. So what we'd have now, let's put this on, we would have now from -1 to 8. So we could say now that y is going to be between -1 and then that's going to be +8. So this now is the range of the function. So that's something that you need to be careful with. In the last few examples, we've been talking about this idea of a maximum or minimum point. It would be fair to believe at this point that we could use differentiation to find the range of a function. If you're going to do this, I strongly advise now that you do a sketch as well, as often it won't give us the full picture. So for example here, if we did, let's take this one right here. So we'll go for this one here. Let's just take this one back here. Now if I did f dashed of x, in this particular case, f dashed of x is going to be 2x minus 4. So 2x minus 4. For now the minimum point, we would set the minimum point now to 0. That would give us 2x minus 4. And solving for x, x would be equal to 2. So that would now give us this point right here. And we could consider now then the f of 2. The f of 2 is going to give us now minus 16. So if we put that in, we get minus 16. And then we consider now that that's going to be the only turning point on the graph. Therefore, we're going to look at values greater than minus 16. We do have to be quite careful with this method. If we look at another example, let's take a cubic function. Let's say the f of x. So let's say f of x is going to be equal to x cubed. And then let's go for, let's say, minus 6x squared. And then we had now minus, let's say we got minus 36x. Now, if I drew a quick sketch of this, what we've got then, that's going to go through the origin. Okay, so let's draw something. This doesn't have to be hugely accurate, but it'll look something like so. So we'll come out now of the third quadrant, we'll come through the origin, we'll turn round, and then we'll go off now, and this will get very large. So we'll be leaving through the first quadrant, we'll be entering now from the third quadrant. So if you went in here, let's say this is y is equal to the f of x. If you now went up and down the y-axis, what values would you see? If we didn't restrict the domain, the answer is all real values. So from this particular case, if we said now the domain, so let's say the domain x belongs to the reals, so x belongs to the reals, and then we could say now the f of x is going to be all real values, or y, and we'll write here, y, the range, we're going to have now that y will belong to the reals. Now, let's consider if we restricted the domain. So if we restricted the domain now for x greater or equal to 0 or x less or equal to 0, we could actually now use the derivative to find the range. Because we can see when it's not got a restricted domain, it's going to kick out all values. So let's go ahead and restrict the domain. Let's say we said now, and we'll write it here, let's say the domain now is going to be x belongs to real, so real numbers, and they are going to be greater or equal to 0. Now, with our sketch, we can see that this is going to do something like so. So how inaccurate this is doesn't really matter at the moment. So we're interested now in the range of the function now where x is going to be now 0 or more. So if we now look at the derivative, so if we do f dashed of x, we can find now the stationary points. So we're going to get 3x squared minus 12x minus 36. So setting this equal to 0, we can see for the cubic, we're going to have two stationary points in this particular case. We're going to have a maximum here and a minimum here. So that's now 3x squared minus 12x minus 36. Let's make our work slightly easier, dividing through by 3x squared minus 4x minus 12. So now we've got, what's that going to give me? That's going to give me x minus 6, and then we're going to have now x plus 2. So this point right here, as inaccurate it is, that's going to give us now the x coordinate here of 6, and this is going to give us now the x coordinate of minus 2. So if we wanted to find the range of the function now when x is restricted in its domain for values greater than 0, we could do now the f of 6. So if we did the f of 6, so subbing in f of 6, 6 cubed is going to give me 216, so we've got 216, minus 6 lots of 6 squared is going to be minus 216, and then minus 6 lots of now 36, which is going to be 216. So let's just check that. Now check we got all of those right, and that looks to give us minus 216. So if we just tidy that up, what's that going to give us? That's just going to give us minus 216, isn't it? F of 6 is going to give us minus 216. So we could say that y will be now greater or equal to minus 216. So that now is the range. So it isn't defined for now all real values here. We've said that it's defined for only values there. Now, if we wanted to do this, we could find if we were going to the other side, because this point now would be a maximum. So if we consider at this stage right here, if we did now the f of minus 2, that's going to give me now minus 8, and then we're going to get minus 24, so minus 24, and then we're going to get plus 72. So what's that going to give me? That's going to give me 72 minus 34, which would give me 38. So this point right here, and again, it's an inaccurate sketch, but it gives us some idea. So this is the point minus 2, comma 38. So if I'd restricted the domain to values here, instead, if I had now less or equal to 0, we could see that the range is going to give me all of these values in this direction right here. So we would say now, in terms of this one, that y is going to be at most now the positive 38. That is if now x is going to be less or equal to 0 with the domain. Here's the range, here's the domain, and we can see that point, like so, going in that direction. This is less likely to occur. You might get some function. They might, for example, give you a function. Let's say they said now that this function looks something like so, and they drew now some function that you've never seen before. So they did that and then scaled it down and went down like so. And they said now find the range, and they might define this y is equal to some function of x. They might give you, for example, now x to the minus 2 plus 3x plus 1, something along those lines. And you would go ahead and differentiate to find the maximum value just here. You would sub this in and then consider now what happens as x gets very large. And you would be guided. So in examples like this, finding now this maximum point and considering that our range is going to be all of those values is a good technique to use. And with the aid of a sketch, you can see. But you will be guided now in these particular cases. So far we've looked at a few different techniques, and it's often a combination of the techniques that can help you find the range of a function. So we looked at the endpoints of a domain. So when we had now for the one-to-one function, a linear function for example, we looked at the endpoints and a sketch helped us. So when we're sketching, look at the endpoints. When we dealt with quadratics, we looked at completing the square or differentiating. I would prefer to complete the square, but differentiating may back up your answer. Then sometimes we will be asked to differentiate the function. You will be led into that, and there won't be anything too crazy when you do that. There are other techniques. I'm trying to sort of avoid doing them. Another example might be if you have a function and you have its inverse. The domain of the inverse is the range of the original and vice versa, and you can work between those. In a later video we will look at some examples of that, and at the moment I just want to avoid those. For now it's testing the endpoints of a domain after you've sketched and realised it's one-to-one. Then you could look at sketching more problematic functions, completing the square, or differentiating. To end up, what we're going to do is look now at finding the other way round. We're going to be given a range and find a domain. So we'll just look at a basic example of this. So let's say now we've got the f of x. Let's take the f of x, and we've been given the f of x, and we'll take a simple linear function of 3x minus 1. And we might be told a range, and the notation we could see is that the f of x is going to be between 5 and now 11. So let's put 5 and 11 on. So we might be asked to find the domain. So let's draw a quick sketch and see what this is going to look like. So we've been given the range. X is the domain, f of x is the range. or x is the domain, y is the range, and you need to be comfortable with switching between the two. So let's have a look at this. This is going to be 3x minus 1. 3x minus 1 is going to look something like that. Now, we've got the range, and the range is going to be between, and we'll just put this here, the range for this particular function here is going to be between 5 and 11. So let's put here, this is going to be 5, and this is going to be 11. So what we've actually got, we don't have all of this, we just have now a portion just here. So all we've got is this part of the function. So let's say now this is y is equal to the f of x, and we want to find the domain. So we've got this point right here and this point here. So the original greeny turquoise line no longer exists. Okay, so let's look at this then. So we know it's 1 to 1, so considering the endpoints, we can say now 3x minus 1 will be equal to 5. So from here, adding 1 divided by 3, we've got now x is equal to 2, which is going to be this point just here, that's 2. And then if we look at this one, now we've got 3x minus 1 will be equal to 11. So adding 1 to both sides, dividing by 3, x is going to be equal to 4. So what we've done with a really basic example here is now found that the domain, and we can write on here, this is the domain, x is going to be between 2 and 4. So that's our domain, and we've simply now worked this back from being given a range. Again, with a question like this, you'll either be given a simple function here, or you will be guided heavily. So there we go, there's a brief introduction to finding the range of a function and also the domain given the range.